All right, so we'll start with the solution of the homework assignment, and we'll start with the easy solution first, and then I'll give you the kind of more difficult solution, but it is the proper way of doing division. Okay, so the long division method. It is kind of difficult using the toy processor because we only got 4 registers to play with, but it can be done. Okay, so we'll go ahead and start with that. The assignment is due today, right? Yeah. Okay. All right. So we'll go ahead and just spend a little bit of time to talk about the easy solution because the successive subtraction method is relatively simple and it's not very difficult to code. So we say register A has the dividend to begin with, register B has the divisor. So the loop that you need is to basically say A, whenever A is greater than or equal to B, stay in the loop. And what you do in the loop is A subtract minus B, you're subtracting B from A, and then you want to increment C by 1 because C is initialized to 0 because register C will be the quotient. So you increment the quotient, you decrement the dividend by the divisor for each iteration, and that's it. This is literally the entire program, okay? So you should probably do this in C first, just to make sure that it does work in C. Now it's time to translate that into assembly. This one is easy, subtract AB, because that's the subtraction where A stores the result of A minus B. This one is just increment C, okay? You're just adding 1 to C. You can use the LDI and then add, that works too, but increment is easier. This one, if you want to, you can do a sub CC, that works. Subtracting C from C will put a 0 into C for sure, but it also changes the flags. So if you have some flags to preserve, don't do the subtraction trick, okay? But if you do not need to preserve the flags, because there are no conditional branches right after this is the quick and easy way to do it. So now the biggest question is, how do we do the loop? So the loop needs a beginning, so we have while begin as the beginning of the loop. It also needs an end, so we have while end here, marking the end of the entire loop. At the end of each iteration, you need an unconditional branch, JMPI, to go back to the very beginning, because that's what makes a loop a loop. And then the only difficult part is how do we deal with, whenever A is, as long as A is greater than or equal to B, stay in the loop. As soon as A is less than B, get out of the loop. Okay? So you need a compare to set the flags. So compare AB is what you need in that particular order. If A is less than B, then we want to get out. So now you have a condition here, I to while end. So the question now is, what do you want to put here? Okay, so we got several options here. If you use C, that is the correct answer. Okay, carry or borrow is the correct answer because A and B are unsigned, right? So you need to use the borrow flag to indicate that A is less than B when A and B are supposed to be unsigned numbers. Yep.
I'm probably getting ahead of myself, but what if A and B were the same number? So wouldn't that set the 0 flag?
That will set the 0 flag, but I'm not paying attention to the 0 flag. If they're the same, then quotient should be 1. You don't want to skip over one iteration when A and B are exactly the same number. So that's why you don't want to use JZI to branch out of the loop. Yep.
I know that since you have to hit the reset button, it resets the registers, but for the C equals 0 line, if I forget to put that, will I get points taken away?
Forget to put?
C equals 0, setting the quotient register to 0.
No, that's fine. Okay. Not a problem.
You can do LDI.
Yeah, you can do LDI too. But the whole point is, when you reset when you reset the simulator, when you click on the reset button, it does reset all the registers. So it's okay. You can use that. Okay. Yep.
So JLI would not.
Now JLI would work in many cases, but it won't work in all cases. So if you use JLI, then you can try to do a 129 divided by 1. It won't work. Because 129 is also representing really big negative value, and that really big negative value minus 1 is going to be negative, right? So it's going to be, so L flag will be set because a really negative value is less than 1. So the L flag will be set, and you'll be getting out of the loop without executing the iteration once. So it will work in most cases, but once you get past 128, and depending on what is your quote, well actually I take it back. As soon as you cross over 128, it's not going to work. Is that okay?
You're missing one line, right? Halt.
Yeah, the hold instruction at the very end. Okay, so that should be it. So Control A, Control C, go back to the assembler. Any issues using the assembler? No? Okay, very good. Probably has some leftover code from yesterday. Yep, that's okay. We'll just get rid of these first. It's a pretty long program, by the way, that you guys will see again. So I'm going to reproduce that code today. Okay, so we paste, wait for the progress bar to be finished, and there's no problem with this code. Go to the RAM file, download as CSV, and we'll call it simple divide, and then we start up the simulator. Should probably write a script to do this because we do it every time in this class. Okay, so we got the simulator. Click reset. Load the program in. And then to test the program, what we do is we go into the register bank, and then we just inject values into register A and register B. We can put a 7E here and put a 1.5 here. Okay, so just for testing purposes. If you are quite sure that your code is going to work, you can just kind of do a Control K to start the clocking, and when they stop changing, just do Control K again to double check your result. If you're not sure that your program is working, you should trace it. Okay. In other words, use the feature over here. Use logging to help track down how the various registers are getting changed. So I'm fairly sure this is working. So I'm going to do a Control K. It's all done. So right now it says it has a 6 as a quotient and 0 as the remainder. And of course I cannot remember the actual dividend. I think it's 7E. 7E. Okay. So now we'll double check by hand. Okay. 7E divided by 1.5. Now we can do all the conversion into base 10 and do the division and use a calculator. But I'm not going to do that. What I'll do instead is I'm going to show you the longhand division, or the manual way of doing division, because we're going to use that next. So we'll go ahead and use that approach right now. And I'm going to move the mic back a little bit. To have cable management issue. Document camera. There we go. Okay. So let me just rotate things a little bit so they look right. Go a little bit higher up. There we go. Focus. Excellent. All right, so we are looking at the division of 7E divided by 1.5 in hexadecimal, and we'll go ahead and convert these to binary number first. This one is 0, 1, 1, 1, E is 1, 1, 1, 0. This one is 0, 0, 0, 1, 0, 1, 0, 1. That's what we're doing as a division. Okay? So the next thing we do is to perform the division itself. And I think I just shot myself in the foot because I may not have enough space to do it. So we'll go ahead and do it over here. So here's our division. The divisor is 0, 0, 0, 1, 0, 1, 0, 1. The dividend is 0, 1, 1, 1, 1, 1, 1, 0. So the longhand or the manual way of doing division is to first look at this digit here of the dividend and ask, do we have at least one divisor in the 0? No. Put a 0 here. 0 times the divisor is what? 0 times anything is 0. So we put a 0 here. We do a subtraction, which ends up with a 0. Surprising? No. Okay. It's just that a lot of times we skip that, right? But that's actually what we are doing when we do division. Then we take this digit of the dividend down here. So we got 0, 1. Then we ask, is 0, 1, does 0, 1 contain at least one of the divisor? No. Okay, put another 0 here then. 0 times the divisor is 0. Okay. You do the subtraction, and then we end up with 0, 1 again. You take the next digit down, like so, and then you ask, is there a divisor in 0, 1, 1? Nope. Put a 0 here. So 0 times the divisor is 0. You do that subtraction, you get 0, 1, 1 back. Then we take the fourth digit from the left, which is a 1 down here, and then we ask, is there a 1 divisor in 0, 1, 1, 1? The answer is no. Okay, 0, 0, 0, 0. Do another subtraction. Okay. You know what? We can do a little bit better than this. We can kind of do a manual zoom and then refocus. Isn't that cool? Okay. So now we move on and we go, okay, so we have after the division, subtraction, we have 0, 1, 1, 1. We take another 1 down, which is from here. And then we ask, is there a divisor in 0, 1, 1, 1, 1? The answer is no. Oh, okay. So we got all zeros here. And then we do the subtraction. Now we got 0, 1, 1, 1, 1. And then we take this 1 down here. We take, sorry, this one. And then finally the answer is, yep, we got one of those. So we say 1, and then we have the divisor here, 0, 1, 0, 1, 0, 1 here. We do the subtraction. 1 minus 1 is a 0. 1 minus 0 is a 1. 1 minus 1 is a 0. 1 minus 0 is a 1. The rest are all 0. So we have 1, 0, 1, 0 left. Then we go here, we take this 1 down to here, and then we ask, do we have another 1 here? Yep, okay, so we have 1, which is 1, 0, 1, 0, 1. Do the subtraction, they're all zeros. Okay? But we are not done yet, because we got this leftover 0. Put that 0 down here, and then we ask, is there one divisor in all zeros? The answer is no. Okay, put a 0 here. 0 times this amount is 0. Do that subtraction. We get all zeros back. This is our remainder. This is our quotient. So the quotient is supposed to be 6 with a remainder of 0. Is that what we got? Yep. So the code did work. Is that okay? Are there any questions about this part? All right, so before I forget, I'm going to pass the row sheet. We haven't passed the row sheet in this class for a while, so it's time to do some trimming, let's just say. Okay, so the next question is, okay, can we do division like this? In other words, can we write a program using the toy processor to do division exactly the way that we should be doing it. What is the advantage of doing division like this instead of the successive subtraction method? It's constant time, right? This one is constant time. In other words, it takes the same amount of time no matter what value you choose as your dividend and what value other than 0 you choose as your divisor. 255 divided by 1 takes 8 steps. 1 divided by 255 takes 8 steps. Okay? It's the same amount of time, or approximately the same. So that's good. Okay, we like that particular aspect of this method. So now the question is, okay, if this is what we want to do, how do we do it? Okay. So what I'll do is I'm going to pan the camera this way so that I have room to display the actual code representing this method of division. So we'll go ahead and use Notepad, a new instance of Notepad, and then we'll put it right here so we can look at the code. But instead of writing the entire code, we'll just write the code to deal with one single bit. Okay? So we have to look at what needs to be done and how do we do it. And by the way, I'm not going to write it in a sequential manner, which means as long as the recorder is on and the fact that we are actually still recording, don't spend your time to write down the code because it's otherwise you'll be distracted. You cannot stay focused on the topic. All right. So what we want to do is to pick a particular line and say, what are we really doing? So apparently there are two things that we are doing. One thing that we are doing is we are taking a bit from the dividend. Take a bit, we'll call this bit B, okay, from dividend. And we want to append B as the least significant bit of some kind of running remainder thing, okay? In other words, this number here, okay, let me use green to represent what I mean by that portion. The remaining portion is this one here. The remaining portion, remaining portion, remaining portion. After the subtraction, this part is the remaining portion, and then this is the one that is shifted in from the dividend, okay? So I'll just call that a remainder. The green arrow on the left-hand side is what I call the remainder, which becomes the actual remainder after the very last subtraction, because after the last subtraction here, it actually becomes the actual remainder. Is that okay? And it appears that we have to compare the remainder to the divisor, right? It also appears that if the remainder is greater than or equal to the divisor, we perform the following. We have to append a 1 to the quotient, and else we append a 0. Is that kind of consistent with what you observed when we were doing the division? Okay. It's kind of what we do in base 10 too, except in base 10, a division is much more complicated because depending on what you choose as your divisor, you might need to go through some mental math just to figure out, okay, is there 5 of these or 6 of these? But in binary, it's easy because you're just comparing. All you're doing is comparing. All right, so we take all of this stuff here, go like, okay, so what are we going to do with this? Taking the bit from the dividend. It seems like we are taking the most significant bit first, right? Because this is the first bit that we use to compare to the divisor. That's the most significant bit. So the question now is, how do I take the most significant bit out of the dividend, which is in register A? I am proposing that we do this. What is that going to do? You're adding A to itself, which means we're doubling the value of A. Okay, that's kind of cool. But where is the most significant bit? In other words, if the most significant bit of A was a 1 to begin with, where is that bit now?
The carry.
In the carry. Okay, very good. So add A to A is really shifting the most significant bit into the carry, which we can check, right? So that's really cool. So in order to append this particular bit from the dividend to the least significant bit of the remainder, we have to do several things. And I have to be careful not to knock the external hard drive out. Okay, so we have to append it to the least significant bit of the remainder, which also means, oh, and also I need to write a comment here and say the remainder is not in register A anymore because register A has a different purpose now. So I'm going to put the remainder in register C. It's register D, sorry. We'll take it, remainder is in register D. To perform the appending of a single bit to the remainder, first thing we need to do is to do, okay, we have to do this, but we cannot do it here. We have to do this earlier. Because if I do it down there, that means I'm destroying the carry flag from add AA. I cannot do that. So in order to append a bit, now we do a JCI to some location. So we JCI to, let's see, LS, okay, register D, LSB equals to a 1. And then I will use a suffix here, a suffix of, underscore, just a single underscore, we'll deal with the suffix later. And then at the label, LSB, DLSB1 underscore, then we're going to say, increment D is going to shift in that one single bit of 1. Is that making any sense? Because when we say add DD, that makes that space, okay? It makes that space of 0 as the least significant bit of D already. By adding 1 to D, we are just turning that 0 into a 1. Is that making any sense? Because add DD guarantees that the least significant bit of D becomes a 0. If that bit is always a 0, adding 1 will only affect bit 0 and none of the other bits of D. Okay, cool. What if the carry bit is a 0? Then we got nothing to do. Okay, so we'll just call that D LSB 0. We're shifting a 0 into LSB, the least significant bit of D, which is basically doing nothing because it's already a 0. I don't have to shift anything into it. So we put that label over here. Now we are done with setting up the remainder. We need to perform the comparison. So now we have to compare the remainder, which is now in D, not in A, to the divisor. The divisor is in register B, so we have to compare it to register B. Now we have to say if the remainder is greater than the divisor, do this, and else we go somewhere else. So the code corresponding to this conditional branch is a JCI. If D is less than B, then we go to this part here. We go to the else branch. So we'll just say else with an underscore as a suffix. So else underscore is here. If we do not perform that JCI, that means we are here. We are now ready to append a 1 to the quotient. Appending 1 to the quotient is the same thing as shifting the quotient to the left by 1 and then incrementing it by 1. Appending a 0 is just shifting it to the left. So either way, we have to shift the quotient to the left, so we might as well just do it here. So we are now saying add C to C, shifting the quotient to the left by 1 bit. The else case here is appending a 0, which means there's nothing to do. But the then case here is to append a 1, which means I have to increment the quotient, which is in register C, by 1. Is that okay? Now, because the else branch has nothing in it, I really don't need an unconditional branch to end if. So I really should be changing this to there's no else to append 0 because the 0 is already shifted in because of this add CC. So this is left shift the quotient. So this means the else really is end if, so we'll just call it end if properly. So end if is here. So are we doing okay so far? That's one single step. So getting back to the document camera, what we are doing is we are shifting in. Okay, we are shifting in this one. We're shifting in this one into this one over here, and then we are comparing the remainder, which is 0, 1, 1 in this case, with the divisor. If it is less than, then we put a 0 corresponding to that bit position in the quotient, and then we do and then we multiply, and then we do the subtraction. Oh, I forgot the subtraction. Did that. So the subtraction needs to be done in here as well. So there's one more thing that we have to do in here. We have to remember to subtract the divisor from the remainder, which is just a SUB subtract instruction, and it has the same order as before. This subtraction here is corresponding to all of these subtractions. Now the else branch has no subtraction to do because we're subtracting 0, which means there's nothing to do. Is that okay? Yep, go ahead.
Sorry, could you spell out again what is in each register? I'm losing track of which register holds which thing.
Okay, sure. So register A is the dividend or parts of. Because we keep left shifting the dividend, which means you keep losing the most significant parts of it. We're shifting the most significant parts into the carry bit so that we can do something with it. So eventually it will all be zeros. Register B is the divisor. Divisor, just like before. Register C is our quotient or parts of. So register C as a quotient is being shifted in from the least significant side. So after we do this 8 times, then whatever we shift in first becomes the most significant bit. In other words, we're still following this order because this 0 is here first. It is the most significant bit of the divisor, of the quotient. But instead of putting it here in place the first time, we're putting it all the way here. But then every single time we perform these subtraction and decide what to shift in, we're shifting the entire number to the left by 1 bit. So after 8 times, this 0 will eventually end up here.
So at the beginning, C is just 8 zeros.
Correct.
Until we start. Okay.
Yep. And then register D is what I call the remainder, which is corresponding to the green arrows. Whatever the green arrow is pointing to is the remainder, including the last one here. Is that okay?
So A becomes the line underneath the green arrows as it changes?
A is still for the most part a dividend, but we are taking parts of A into, we're shifting parts of A into the remainder. Okay, so the first one is by default here. Okay, so it's not represented here in this division. This is shifted in through here, and this one is shifted into here. This one is shifted into here, and this one is shifted here. This one is down here. I need a ruler, but I think I'm doing an okay job without a ruler. There we go. Is that making any sense? But I cannot just copy the bits when I'm dealing with the code. So instead of copying individual bits in their original position, I'm shifting the dividend to the left, one step at a time, so that whatever I shift out into the carry is the actual bit that I need to shift into the remainder. Is that okay? So what you see in the code to the right-hand side represents one single step. Okay, shifting in using the red arrow is the first part. Doing the compare, the subtract, compare is the second part to determine the quotient bit, and then the subtraction is the third. Is that okay or not? Okay. All right. So it would appear that I need to repeat this code 8 times. Right? So now the question is, if this is actually what you need to do at work, what are you going to do? You need to repeat this code exactly 8 times. I don't want to do a loop here because I have used up all the registers already. I don't have anything left over for counting purposes. Now I could use a separate RAM-based variable just for counting, but that means I'm going to lose one of the registers because you have to use at least one register to deal with a variable. We'll need 2 in order to update it. So it's going to be troublesome because I have to keep constantly swap in and swap out all those things. So that's why I'm not going to use a loop here. I'm going to keep this code and just replicate it 8 times. Okay. So the first possible solution, if this is what you need to do at work, is to repeat this code 8 times, is copy and paste it 8 times, and then go back and change the underscore to _0 for the first one, _1 for the second one, _2 for the third one, and so on. There are a few inherent problems with that approach. One is it is very boring. Okay, that's my #1 issue with that approach, is it's extremely boring. 2 is, what if you mistakenly forget to change one of the labels? Or you have a typo. Instead of _2, you mistype it as _1. Then it will go to the wrong label. The assembler says, yeah, there's such a label earlier, so it's not going to complain, but your code is not going to work, right? I don't like those problems. Third is, if this code has a problem, if I forget to do something here, I got 8 copies to fix. If I forget to fix one of the 8 copies, the assembler doesn't care, right? The code just won't run correctly. Then I have to really go through it line by line, going through 8 pieces of the same code to make sure that they're consistent. I don't want to do that either. So what do? I don't want to turn it into a subroutine because we don't have enough registers to play with to turn it into a subroutine. PHP. So we're going to abuse PHP for this purpose. Okay. Or any scripting language, but since I have been teaching PHP recently, it is fresh in my mind. I know how to use PHP. So I'm going to use PHP here. Okay, wrong password. Beer. There we go. Aptitude install PHP. This is why I like Linux, and particularly Debian-based or any distro that can give you a tool to do this. Because if you want to install PHP, one command line, done. Okay, we are done with installing PHP. You can do this in C too. Okay, it's just not as easy because I like PHP because you can do a single print with line breaking included. I don't think C can handle that. So get out of this and get back into here. So I'm going to save this program, but when I save it, I'm not going to save it as a C code or assembly code. I'm going to save it with a PHP extension. So I'm going to call this divide.php in the temp folder. And I will close this because I don't like to edit PHP code in Notepad. I like something that has syntax highlighting. So I'm going to use vi divide.php. And then we go, this is how you begin the script portion of a PHP script. This is how you end it. And in between all of this stuff here, we just say print all of this the way it is. Single quote here to end the entire thing. And this is something that I don't think you can do with C, because I think double quoting cannot cross lines. in C and C++. Is that right or not? Nobody knows?
I think I've
You
tried it.
can, but you,
You
I
do
don't
it
remember
manually.
what you have to do.
So does it take the end of line correctly when you cross?
I don't
I think,
think
yeah.
so.
Hmm?
I don't think so, but I
It
would
just
have.
ignores the end line, doesn't
Does it ignore the end line? Can you?
it? Just open up the-
Okay.
It like treats it as a giant
Yeah.
string.
So when it prints, it is still on one single line. There are no line feeds.
Right.
Okay. Okay. So I like this because it keeps all the line feeds, all the end of lines. Okay. So now we go back here and say everywhere there's a single underscore, we'll replace it with a variable. And this is also this is why I like a VI, because in VI you can do a substitution, and you basically say replace every single underscore with underscore and then a dollar and an I, because that represents a variable in PHP. So now we have $I to be expanded in place in the string. And then what else do we need is $I is initialized to 0, $I is less than 8, plus $I. So $I is nothing more than just an integer variable in a loop, and this is my entire loop. So what I would end up doing is I would do it 8 times. The first time $I is 0, the second time $I is 1, and so on. So this the output of this PHP script is not HTML. Is that okay? Absolutely. Okay. Who says PHP has to crank out HTML code? Nobody. Okay. So to me, it's really just a scripting language to crank out all this code. So we say PHP divide.php, and you can see the output is rather long and boring because it is just the same piece of code repeated 8 times. Okay. So now we can say, okay, let's do it one more time, but this time we want to redirect the output of PHP to divide.ttpasm, text toy processor assembly language. Okay. And then we look at the actual code in TTPASM, and you might notice that VI knows how to highlight the instructions, comments, and stuff like that, even though this is an architecture that doesn't exist other than this class. That's because I defined the syntax highlighting rules for VI for this extension. We lack one instruction at the end, which is the halt instruction. Well, there are 2. There's the halt instruction, and it's also the CPR instruction, because according to the homework assignment, I want the remainder to be in register A, but not in D. So we have to copy register D to register A to meet the requirements of the homework assignment. Is that okay? So now I think we got everything here. And then we have the notepad again, because we have to copy and paste into the assembler. Whoop. Not notepad, mousepad. There we go. Control A, Control C, and then we go back to the browser in a different window, which is right here. Okay, go back to source and go to line 1. Just overwrite the entire thing. Wait until the bar is done. Look for errors. Okay, we don't have any errors here. The other quick way to look for errors is to go to RAM file. If you do have any errors, this will display there are errors. And then Logisim won't take it as an input file anymore. So we save this one.
Bless you.
Okay, as divide.csv. And then we go back to Logisim, which is in another window, another desktop right here. We reset the whole thing. Control R would actually reset the entire thing too, but that also resets the RAM content, which is what I want this time. So that's okay. So we go to RAM, we load image, and this time we want divide.csv, which is here. And this program is actually pretty big. If you look at it, it's actually pretty big. It took up more than 1/3 of the space available in the toy processor. But that's okay. I mean, the toy processor it only has 256 bytes to begin with. Okay, this took up up to what 6 I would say that's 69, right? 69-ish. So that's 6 times 16 plus 9, which is about 100 something bytes. Now the question is, does it work? So we go back here, we look at the register bank, and then we can test it with something the same, okay, 7E. But this time we'll change the divisor to 1-4 instead of 1-5. Okay. And then we'll do a Control K, let it run, Control K again. So it says, you know, the quotient is a 6 with a remainder of 6. So this time we'll double check, you know, whether that is the case or not. So we'll switch back to the document camera. We got 7E divided by 1/4 in hexadecimal. Okay. And we'll pan the document camera back so that we can see the entire thing. I'm not going to do another binary division because, you know, I think once is enough, right? Once you get the idea, you know, that's good. So this time we'll do the division in hexadecimal. Okay, 7E divided by 1/4. There's a 0 here, so we get 7 back. Then we have 7E. So how many 1/4s do we have in 7E in hexadecimal? So we get 6. 6 will do. 6 times 4 is what we call 24 in base 10, but 24 in base 10 is 1/8 in hexadecimal. Because the 1 is representing 16, 16 plus 8 is in fact 24. 6 times 1 is 6, and then we have a carry of 1, this is 7/8. E minus 8 is the same thing as 14 minus 8, which is 6. So 6 with a remainder of 6 is in fact correct. Is that okay? It just so happens that the quotient and the remainder are the same in this case. Are we doing okay so far with this? Are we ready for the next homework assignment? Yeah? No, no. Okay, so before we present the next homework assignment, I'm going to present the same program that we did before. Did we do the subtract or the add? Let's do the subtract one. Okay. All right, so what we want to do is to go back and understand how parameters are passed. Okay, so that's the first thing we need to do. All right, so I can do this using the document camera because I can actually highlight stuff easier this way. So let's just say that we want to perform this operation. This is the subroutine called subtract, and it is given two parameters, x and y. And the only thing I wanted to do is to return x minus y. This is also in the notes, so there's no need to worry. This is all it's all explained in the notes. So now the question is, how do we implement the subtraction subroutine? Okay. So the way it is implemented is we have sub colon to indicate as a label to mark the entry point of the subroutine. And then we have to get the value of x, which means we need to do a CPR. We can use any other register at this point because we are not quite at the point of returning, so we can use register A, B, or C for the intermediate stuff inside the subroutine. So I'm going to use C as a copy of D. So at this point, C points to the return address. Is that okay? Oh, okay. That's better? Is that okay? Because the stack pointer is supposed to be pointing at the return address at the entry point of a subroutine. But that's not what I want. I want C to point to the parameters. So then I do an increment C. When I increment the C, then C is no longer pointing to the return address. Now it is pointing to X. That's one of the things that I need. Cool. Let's do a load instruction here. Put it into register A. So now A is X. A is parameter X. Is that okay? And then we increment C one more time, and it is going to be the address of Y. And we need that too. Put it into B. Okay, so now B is parameter Y. Once we have A, which is parameter X, and B, which is parameter Y, we can do the actual subtraction. So we say subtract B from A, so that A is now X minus Y, which is cool because this is how we return a value. For anything that is returning a scalar, it is returned through register A in the toy processor. Okay, so we got the calculation done. So it's time to return. I got nothing else to do at this point. It's time to return. So when we return, we know that D is still pointing to the return address. So I'm going to say LD B D. So the B is now the return address. Then we increment D to deallocate a byte on the stack. So we say deallocate byte, and then we can do a JMPB to continue execution in caller. Is that okay? It's the same code in the notes. Okay, there's nothing new here. I'm just explaining it, on the fly. Is that good? Okay. So the next question now is, what do we do when we call? So let's just say that, from the caller's perspective, somewhere in main, okay, so somewhere in main, we say, I want my register C, okay, from main's perspective, I want my register C to be the result of the subtraction of, 45 and subtracting 125 from 45. This is what main wants to do. So the question now is, how do we do this in from main's perspective? Do you guys remember? How do we pass parameters?
Push them on the stack.
Push them on the stack. But the order is important, because if I'm using add, hey, if I got the wrong order, it will still work. But if I'm doing subtraction, I have to make sure that it is pushed in the right order. So from this part here, okay, just from the definition of the subroutine, which one has the higher address? Does X have the higher address, or does Y have the higher address? Y has the higher address, which means which one has to be pushed first? Y has to be pushed first. Because the stack grows down. Remember, the earlier item that you push on the stack has a higher address. The last item that you push on the stack has the lowest address. We want X to have the lower address, so that's why we have to push X last, as opposed to Y. So that's why in this case, the code corresponding to this call is LDI. You can use A, okay, so because at this point we are just setting up for the subroutine. A has no special meaning. So LDIA with 125, decrement D to allocate space on the stack, STD with A. So this would actually store the 125 on the stack. LDIA with the other number, which is 45, decrement D, STDA. So this is going to push 45 on the stack. At this point, there's only one thing left to do, which is storing the return address on the stack. So now we have return address 1, which we'll define later. Decrement D again to allocate another byte on stack. Store the return address on the stack, which is now in, oops, I forgot. A comma over there. So we store register A where D is pointing to in RAM. Now we can do a JMPI instruction to continue execution in the subroutine. So we JMPI to sub. We wanted to return to this point here, so we want to define RET_ADDR1 over here. That will be the continuation. The return value is always in register A, but I wanted to put it in register C, so we just need a CPR instruction to accomplish that. So that becomes the caller's code. Are we doing okay so far with this? Okay, so if you have questions about this, in terms of, I don't know what is on the stack and what is happening to each register as we execute this code, I have two recommendations. The first one is to use logic_sim, okay? But when you execute this program, you want to trace or track down the values of the program counter. You want to track down the value of all the registers as well as the last few locations in RAM. I would track down the last 4. The 4th location from the back, from the highest memory location, should not change because we shouldn't be touching that. But that will basically show you what is actually happening. The second way to track down this program is to use a spreadsheet. Okay? You guys know that I have a special knack of abusing a spreadsheet to do things that I'm not supposed to do, right? Okay, so we'll do it this way. We'll do it one time, just so that you have another tool to help you understand what happens on the stack. Especially when we get to more complicated examples, that might actually be quite handy. So we go to the spreadsheet and say, okay, let's make another one. So I'm going to make a new spreadsheet. And I'm just thinking about what to do with the line numbers and the program, because I need to display both the trace and the source code at the same time. Okay, we'll do it this way. So we'll go ahead and actually edit the code in here. So vim sub.ttpasm. The first instruction is a LDID with a 0 to initialize the stack pointer. I'm not going to put any comments here because I don't want it to take up too much space width-wise. So I'm just going to put in the code here. LDI A125, decrement D. Oh, decrement is not highlighted. STD with A. LDIA with the other number, which is 45. I'm just copying whatever I had on my document camera. Decrement D again. Store that onto the stack. LDIA with return address 1. Decrement D. STD with A. And then we do a JMPI to sub. Upon returning to ADDR1, we do a CPR CA and halt. Yep.
Or you continue, the third decrement is decrement C.
Oh, okay, thank you. All right, so.
You said D, but you froze.
Okay. So the subroutine, on the other hand, is CPR CD, increment C, LDA C, increment C again, LDB C, and then we have sub AB, LDB D, increment D, and JMPB. Right, there we go. And we'll change the size of this window and also enable line numbers, so we can refer to the line numbers here. And then we go to this side, change the spreadsheet so it looks like this. Okay, so this is something that I did in cisp310, is to trace a program line by line using a spreadsheet. So on the spreadsheet side, each row is representing a slice of time, and each column is representing the content of a register or the content of a particular location in RAM. Is that okay? So I will label column A as line number, which refers to the actual line number that we observe here. Column B is going to represent register A, the content in register A, register B, register C, register D, and then column F is location 255, okay? So we'll just call this RAM location 255. Oh, wrong place. Let's cut, paste, there we go. RAM location 254. And RAM location 253. And we'll even track RAM location 252, which should not be touched by this program. Okay. And then we'll shrink the columns so it's easier to look at. Now we track the program. Line number 1, we'll put a 0 into register D. Line 2 is doesn't do anything, so we'll skip to line 3. Because line 2 is just a label, it doesn't really do anything. It's just saying that, okay, the following instruction also has a label of main. So that doesn't do anything. Line 3 stores a 125 into register A. Line 4 decrements D, so it becomes 255. Line 5 is saying, okay, go to RAM location, basically it's RAM in square bracket D is indexing. So RAM location 255 stores 125. Location 6 is to load 45 into register A. Line 7 is decrementing D, so D is 254. Line 8 is storing A into D. D is 254, so RAM 254 is updated to 45. Line 9 is to put that label, return address 1 into register A. So I'm just going to say this is RA1, return address 1. And because I'm not going to resolve that label, yeah, that'll be fine. So now we move on to line 10. We decrement the stack pointer to 253. Line 11 is going to store that into this location. RA1 is going to be stored here. Then we go to line 12. Line 12 by itself doesn't really do much, but it changes the path of execution. So the next line that we're going to execute is not going to be line 13 anymore. It's going to be line 18 because it is continuing execution at the label of sub, but sub doesn't really do anything. Are we still doing okay so far? On line 18, we copy register D to register C. So now register C also has 253. On line 19, we increment C, so that becomes 254. On line 20, we go to that location 254, retrieve the content and put it into register A. So register A is now getting the content of column G, which is 45. On line 21, we increment D, so it becomes 255. On line 22, we store that into B. So register B is going to get RAM in square bracket 255, which has the content of 125, like so. And then on line 23, we perform the subtraction. It is 45 minus 125, which is negative 80. And then we go to line 24. Line 24 is going to retrieve, it's using register D, which is still 253. RAM location 253 has RA1. That is what we're going to put into register B, RA1. And line 25 is incrementing the stack pointer. So the stack pointer goes back to 254. I forgot to do two things here. I forgot to clean up the stack. So after the CPR, there should be 2 additional lines of incrementing the stack pointer. But I'm not going to mess it up here because otherwise the line numbers won't work. So we go to line 26. Line 26 by itself doesn't do a single thing. It changes the program counter. But the next line that we execute is no longer on line 27 because we don't have a line 27 in the program. It continues to execute where register B is pointing to, which is return address 1, the label. Return address 1 is over here on line 13. It doesn't do a single thing, but line 14 does something. So line 14 is going to copy register A to register C. So register C is now going to be negative 80. And then that concludes the whole trace. We're done. But I am missing to increment D between line 14 and line 15 because whatever is currently on the stack is no longer really useful. So the 125 and the 45 should be deallocated from the stack at this point. Is that okay? I mean, is that helping you guys understand what is happening with the registers and what's happening on the stack? That's cool? All right. So it's time to give you your homework assignment, which is based on this, okay? I was about to do it in my office, but then we got some questions and I didn't have enough time to actually type out the homework assignment. I get enough time to do it now. Okay. So add a new assignment. And we'll call this nested call. Okay. I can't deal with this really large add item. Okay. Click it and edit. There we go. All right. So I'm gonna put this here and say. Okay, assume sub is implemented. Okay, here we go. As follows. Okay. In the attached file. That's better, I think. What is the name of this file? Sub.ttpsm. Okay, there we go. Write a TTP-ASM program that performs the following. We'll just say that I want register A to be 5 minus 1 minus 6 minus 4. Okay, there we go. That's what I want you to do. Okay. Steps to do it. I'm going to use the bulleted point. Where's the bulleted point? Right there. Okay. So the steps to do this is to write your code at the beginning of the source file. Copy and paste the subroutine code to the end of your source file. Okay. Make sure there is a halt instruction at the end of your code, and that's it. Yep.
When you have like A equals sub, do you mean to put a third sub? Because it looks like you're gonna do like sub.
Oh right, there's another sub here. Thank you.
Yeah.
There's another sub here.
You want to make that call into assembly?
Huh? Yep. Implement that whole thing in assembly.
Yeah.
So now you have to think about the sequence of things, right? What are you going to do when you do this by hand? So the first thing you do is to say, okay, we cannot perform this sub, right? What you cannot perform, don't do anything, right? No need to worry about what you cannot do at this point. What you can do is to say, oh, I know how to do a call subtraction with 5 and 1 as parameters, but do you want to do that first? Really? Maybe not, right? Because that's the first argument. We want to do this first. Can we do it now? Yep, we know what is 6, we know what is 4, we just call subtract, right? Whatever that returns becomes the second argument of the outer sub. You might want to find a place to put it, right? Then you perform the first one, and you find a place to put it to prepare for the outer sub. You call the outer sub. When this is all done, the result is automatically in A already, so that assignment is useless. And then you put a halt instruction after the entire thing. That's your homework assignment. So the homework assignment is not testing whether you can write subroutines or not. It is really testing whether you can call subroutines in a nested fashion or not. This is nested call. So here's the question. How many stack locations should you end up using when you're implementing this program? Just conceptually, you don't have to worry about the actual instructions, but conceptually, how many stack locations are you going to use? Okay, so I'm going to do this on the whiteboard. So if you want to write it down, you might want to write it down. Okay, so you're going to set up the first call. I'm not even going to give you the actual numbers because that would be just like giving away everything. Okay, so you basically have the second argument, first argument, return address, call it the first time, right? It will come back with an answer in register A. You clean up the stack, so the stack will become empty again. Then you have to remember that thing on the stack. It takes up 1 space on the stack. Then you set up for the second call of the sub. So now you basically go, okay, we need second argument, first argument, return address. That's for the second call. The second call returns, right? With the answer in register A, you clean up the stack, but only the green portion. So now the stack only has 1 single red part left over. But you also want to use use up another byte to set up for the third call to sub. Is that okay? So in the third call to sub, you have all of these components here, both parameters are now on the stack. You just need the return address to be on the stack. So the black one is the return address. You call sub the third time, you come back, you clean up everything on the stack, and you're done. Because register A automatically has the result of the subtraction. Is that okay? So the color coding is really just representing, what red represents the first call, green represents the second call, black represents the third call, or what you're adding to the stack for the third call. So that means the entire thing should use up only 4 positions on the stack. Because if you think about it, some people say, okay, we have 3 calls, right? Each call is going to take up 3 positions, so that means it's going to take up 3 times 3, which is 9 positions on the stack. That is not the case, because we reclaim the space that is used each time we return from the subroutine. So all the green stuff is reclaimed, but you want to push something on the stack to prepare for the third call. That's why we have that thing here. Is that okay? So the instructions involved is kind of tedious. There's a lot of stuff that you have to do with register D, decrement, 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 increment, decrement, 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 increment, increment, and so on and so forth. So the concept should not be very difficult. Okay, so you're going to turn it in. Okay, turn in the source code of this program, and then I'll put in the attachment. So let's make this a 20-point homework assignment, and it's in the assignment part, online submission with a file upload, and I need to attach my code here too, so do next week. Ooh, November already, time flies. But this is one of the semesters that I can actually cover all the topics that I wanted to cover. And this class starts at
10:30.
10:30. Okay. All right. And I'm missing the attachment.
Yeah.
Okay, where do I put the attachment? I know there's a place to attach.
Under level settings, give or take.
It's all the way at the bottom.
No. It should be around here. If it's not here, I can always put it somewhere else. Okay, well,
Oh, it's at the
Files.
huh?
Files.
Files.
There's,
Ah. Okay, all the way down.
yeah.
Okay.
It's weird that they put it under the publish button.
Yeah.
Right there.
Ugh.
It is a little strange that it's under the publish button.
It's
Or the
Canvas.
same.
Canvas. Yep, Moodle is on in this last semester. So I'm planning for a Moodle memorial party at the end of the semester. So I'm including the whole file. In other words, everything in here is included. So I'm giving you even this code here, as a, well, let's just call it a starting point. But remember, okay, I'm gonna do it one more time. We are supposed to increment the stack pointer twice to reclaim that space. So I'm gonna put it here so that no one can say that, but yours code is missing that too.
Since your instruction is to append the sub at the end, I guess you could just say the sub portion of the sub file. In your instructions, you say to append the
Okay, so
copy and
the
paste the subroutine. Oh, the subroutine. Okay, you're good.
yep.
You're good.
So basically, what you guys will be doing is to replace this portion with whatever code you need to do.
Yeah.
That's it. And I think most of you have a pretty good idea of what you need to do. It's just the tedious part of actually doing it and debugging the code that's going to take you time. Is that okay? Cool. All right. So I'm going to stop the lecture today a little bit early. So stop streaming.